Carbon is the organic element. The presence of carbon lets you know something is an organic compound. Because all things are made of cells, and 25% of cells are made of carbon compounds, the study of carbon is extremely important to biology.
But why is carbon so important? Why is it such a foundational atom to life? What makes it so important? Well, it's the basic building block of life. You can't be a good building block if you only form one or two bonds. Carbon atoms are very versatile. They are tetravalent, which means they're able to make 4 stable covalent bonds. The only other tetravalent things are going to be the ones below carbon on the periodic table. So silicon-based life, maybe, we don't know. Because carbon is tetravalent, there are a lot of isomers, which are molecules with the same molecular formula, but different structures. From the Greek isos, meaning equal, and meros, meaning part, isomers contain the same number of atoms of each element, but have different arrangements of their atoms in space. Isomers do not necessarily share similar properties unless they also have the same functional groups, which we'll talk about in a bit. There are many different classes of isomers, which you can see in the chart here below. 2 main forms, though, are the structural isomers, or the constitutional isomers, and the stereoisomers. Structural isomers are atoms and functional groups that are joined together in different ways. Stereoisomers, the bonds are the same, but the geometric positioning of the atoms is very different. That doesn't sound like it's going to be a big deal, but isomers have different structures. Therefore, they have different functions and different chemical properties. One example from the past is thalidomide. There's 2 stereoisomers to thalidomide, an S and an R. If you look, the only difference is the angles. The bonds are the same. But what we find is that one version of thalidomide reduced morning sickness, but the other caused severe birth defects. Outside of isomers, carbon is very diverse and can make bonds with many elements and molecules, but a very small change can alter the function a great deal. The example that I have here is ethane and ethanol. You can see the difference is that ethanol has an O attached to the carbon instead of just the hydrogen. But why does that matter? Well, ethane is nonpolar because everything is equal in electronegativity. But oxygen is a lot more electronegative, and so it makes that molecule polar. It makes it unbalanced, unsymmetrical. So what happens is ethane is a gas, but ethanol is a liquid, and all I did was add oxygen. The properties of an organic molecule are not solely determined by the carbon skeleton, but also the arrangements of atoms attached to it. Certain groupings of atoms called functional groups are found to recur time and time again in many different molecules, often having important roles in the reactions a molecule can participate in. So they're the basic building blocks for biological molecules, and they give each one distinctive properties. My example here is the male and female sex hormones, testosterone versus estradiol. If you look, they're very, very similar. But what happens is this methyl group right here is oxidized by an enzyme, and when that happens, it converts testosterone into estradiol. So it turns a male hormone into a female hormone. Small changes, big effects. Now, the basic functions of the functional groups are described here on the right, and we'll talk more about them in class. But there are 7 major ones in biology. There's way more than 7 in organic chemistry. But by changing which functional group you add, you're going to affect reactivity, you're going to alter polarity, you're going to alter solubility in water, you're going to change the pH. So which functional groups you use has major effects on the organism. As we saw earlier in our levels of organization, atoms become molecules, and they do that by becoming polymers. Polymers are long molecules built by linking a chain of repeating smaller units, monomers. Great variety of polymers can be built from a very small set of monomers. Think about it like the letters in the alphabet making all of the different words that we have. So each cell has millions of different macromolecules. But how do those molecules come together? Well, there's two basic reactions that occur. The dehydration synthesis reaction is a condensation reaction. It joins monomers by taking water out. So one monomer provides an OH, the other monomer provides an H. Together these form water. Now this process will require energy and enzymes to occur, but they will make a bond. So you remove water to make a bond. Hydrolysis is the opposite. You add water to break a bond. You use H2O to break apart the monomers. The H2O is split into H and OH, and where the covalent bond used to be, those take its place. Energy is stored in the bonds that link these units together. The amount of energy stored varies with the type of molecule formed. As a result, not all organic molecules have the same amount of energy available for use by the organism, but the basic process of joining and separating is the same. So by doing dehydration synthesis, you're able to build macromolecules. And in biology, there are four major classes of macromolecule: the carbohydrate, the lipid, the protein, and the nucleic acid. Using the acronym from earlier, SNOPS, you can tell the four major classes apart. Carbohydrates will be made of CH and O in a 1 to 2 to 1 relationship. Lipids will be made of CH and O, but you will not see the 1 to 2 to 1 relationship. Proteins are made of CH, N, O, and S, so they incorporate sulfur, unlike any of the other four. And nucleic acids are made of CHNO&P, so they incorporate phosphorus, unlike any of the other ones. So using this basic rule of thumb, if I give you the molecular formula of a macromolecule, you should be able to tell me which class it belongs to.